Good morning, everyone. In this class, I will make a quick revision on chapter 3. Please note that this chapter already done before the lockdown in the normal classes. So I'm gonna be quick. It's just a revision class. Chapter 3 is speaking about pressure and hydrostatic principles. We have 6 sections in this chapter. Pressure, introduction to pressure, then pressure measurement devices. Section number 3 is about fluid statics. Then we're gonna speak about hydrostatic forces in submerged plane surfaces. And section number 5 about hydrostatic forces in submerged curved surfaces. The last section is about buoyancy and stability. Right. So what is pressure? In general, we have a concept for the pressure. Pressure is force over area. But in fluid and in liquids, this force we are dealing with normal forces. So when we calculate the pressure, it must be the normal forces over the unit area. What is the unit that used to measure the pressure? It's a Pascal, which is equal 1 Newton over meter square. We have many other units like bar, etc. So mainly we gonna deal with Pascal, which is in Newton over meter square, right? We have three concepts to describe the pressure. We have absolute pressure, right? We have gauge pressure, we have vacuum pressure. We need to understand these three concepts. Please look at these figures here. It will help you to understand. In few words, you see absolute pressure, meaning that it's the actual pressure, the real pressure. Gauge pressure, meaning that the difference between absolute pressure and local atmospheric pressure or any other reference. So gauge pressure is something we measure. So mainly it will be the difference between absolute pressure and the atmospheric pressure. Vacuum pressure, it's the pressure that will be below the atmospheric pressure, right? Look at these figures, will help you to understand this with this equation. This section already described before. You have simple example here. I want, so just you can do it based on the equation here, please. Now the concept of a pressure in a liquid, that you see guys here, we have, when we have water drop inside the water body, we will have a pressure from all sides, right, as you see in the figure. So if we do like force analysis, summation f of x must be 0 because this water drop is stable, there is no movement. And if we do this in z direction, in z axis, it will be 0. I won't go inside these details again. You can read it, and if you have any problem you can ask me. What we need now, we need to know this slide very well. If we have a water body, we must know that the gauge pressure are proportionally increased with increasing the depth. Look at this figure. Look at this equation. This is how we're gonna measure the pressure here, right? So if we go to the surface here, the pressure here is only the atmospheric pressure. If I go deeply, if I go down, you will find a new value of pressure which is equal rho GH. So that's why When we go deep in water or in ocean, we have extra pressure over our bodies, etc. If you look at this plate, you will find the pressure at the top side is higher than the pressure at the bottom side. Why? Because we have delta Z here. See, we have delta Z. Delta Z meaning that the depth of the bottom side is higher than the depth of the top side, meaning that we have extra pressure. Some details you can read. If we apply the same concept for air, we still have the same concept, but when you say rho GH for air, it's very little, it's neglected, not like water, because density of air is very little. It's about 1.5 kilogram per meter cube, not like water, which is about 1000 kilogram per meter cube. So we can say that the extra pressure for a small distance in air is negligible because of a small density of air. Okay. Now look at this figure. This figure show you. You see we have many points. We have A, we have B, we have C, D, E, etc. You will see that all of these points have same depth H. So the pressure over them are same. But if you go to the I point, no, we have extra depth. So the pressure at I is bigger than G and F, etc. So guys, regardless the shape of the surface, in calculating the pressure, we only care about the depth and the liquid. So that's why if you go to the point number H, it's not like the pressure here in H, not like I, because we have mercury. Mercury, guys, density of mercury is 13,600 kilogram over meter cube, which is much more than water. So the pressure that produced by mercury is 13.6 times more than the pressure produced by water. So we must be careful when we calculate the pressure. It's rho GH, right? But we must be careful about rho and H. Okay. What about Pascal law? We need to know how is the pressure distributed inside a confined liquid. We need to know that we have two kinds of systems as we discussed in chapter 1. We have a closed system and open system. Let's say we have a closed system, we have confined liquid inside that system. We have Pascal law here, the pressure applied to a confined fluid increase the pressure through by the same amount. So here the pressure distributed in same amount, meaning that we're gonna have different forces for different areas. So, and this is very clear in if we use it for the hydraulic jack, or hydraulic lift, you're gonna use small forces. You applied it over a small area, it will produce high pressure. This pressure will be um, increased or applied to another area, like bigger area, with bigger forces, with bigger force, because pressure is gonna be same. Pressure P1 is gonna equal P2. So look at this figure here. We must know that this only applicable for confined system when the liquid is confined. So if I have force, normal force, like by by feet or leg, whatever, it's about few kilonewtons. So if I apply this force over a small area, I'm gonna produce pressure B1. This pressure will convert it to a big force if I apply it for a big area or bigger area, as you can see in the figure. Look at the equations, you will see this concept. Okay. Section 2. How we are measuring the pressure. You see, guys, we have different kind of equipment and devices to measure the pressure. The first one, the barometer, which is used to measure the atmospheric pressure. The concept is very simple and very easy. When we have any surface, any liquid, the pressure and in the external point will be the atmospheric pressure. So I apply vacuum tube, then the liquid will rise up till it's create a pressure equal to the atmospheric pressure. Then that's how can I measure the atmospheric pressure using the barometer. We discussed this method in details in the class. Please read. If you don't understand, you go to the textbook, you will find all details there. Okay, so this is a very quick example, direct, simple example done in the class. I want to repeat it again. It's very simple, just read it. The second equipment that we are using to measure the pressure is manometer, which is mainly used to measure the gauge pressure in pipe flows, in any water system, etc. The concept of this, we have two kinds of manometer, single liquid manometer and multi fluid manometer, right? So the concept is about to make a difference. So let's say to make a difference in the level between the system that I gonna measure the pressure and the atmospheric pressure or any other reference. So look at this. This is a very basic manometer. Let's say I have like gas here, gas cylinder, any gas pipe, whatever. So I connect the manometer to the gas. So if the gas pressure is higher than the atmospheric pressure, as you see here, the liquid in this manometer will rise up in this side, meaning that I have extra pressure more than the atmospheric pressure because I have atmospheric pressure here, right? If the atmospheric pressure higher than the gas pressure here inside the cylinder or this pipe or whatever, you will see the liquid going down this side and rising up here, right? So this is how we can use the manometer to measure the pressure inside gas cylinder. If we have a fluid flow, we can use also manometer to measure the pressure difference between point 1 and point 2. We discussed this method in the class, but I'm gonna repeat it very quickly. Let's say this is the manometer. I connect it to point 1 and point 2. So for sure the pressure here will be bigger because after flow we have some friction losses, other losses, so the pressure will be here is less. So what we need to know, we're gonna make equation. We have this equation. So to measure the pressure at 1 here, P1 plus rho g, the distance till A. We have this is the line here. So we have A and H, Then minus rho 2, which is the liquid, right? GH, this distance. I'm gonna describe this method in next example in details. So minus P1, which is the liquid, which is the water as example here, GA, this distance. This equation equal, all these terms gonna equal B2. Right. I received some inquiries in email about how we can understand this concept. I gonna show you it in detail in the next example. Just hold on. So we can measure the difference between by simple mathematics. P1 minus P2 is gonna equal ρ2 minus ρ1 GH. That's it. This is a photo of manometer. A simple example. Let me go to this example, guys. I need you to understand this example very well. I won't repeat it again. You need to, I will describe the method here, then we will have also another example in the problems later. Right. So the concept, guys, about how we can derive the equation for manometer, multi-fluid manometer. Listen carefully. You must start by the left side. So look at this system here. We have water here, then we have oil, then we have mercury. What I need to know, I need to calculate the difference between, as example, pressure 1 and the pressure 2. Or I need to know pressure 1. We should be able to do many things, right? So what you're gonna do, simple. You must start with the left side and name or call this point as 1. So P1 here, which is the pressure inside the water tank. This is P1. Then you will look at the next liquid, the following liquid, which is oil, right? So this is oil. Where is the surface change? It's here, right? Look. So all this is water, so I don't care now. I care only about the level difference between the water here and the following liquid, which is oil. So if the level is less than the original level, as you see here, I need to use positive. Then rho GH. Okay. Again, I gonna look at the where is the changing between the liquids. So let's say I have water, I have oil, I have mercury. I only care about the level or the depth or the level between the two oils, or sorry, the two fluids, water and oil here. So this is the water surface and this is the oil surface. So water surface is higher than oil surface, so I must use positive. Raw water, I gonna use the raw for the first, for the original, for the left liquid. G is G and H1 is the difference between them. That's number one. Then I look again, I see the next liquid is mercury. Oh, what is the level between oil and mercury? It's here. So it's a drop, meaning that the level of oil is low. The level of mercury, the level between mercury and oil is lower than the starting level of the oil, meaning that I gonna use positive raw oil GH2. Then The last level is mercury here, which is, then we have air, so it's still fluid. So I can see that this level here is, the end level is higher than the start level, so I use negative. Raw mercury G H3. All this term gonna equal B2 here, which is equal B atmosphere, by the way. Sometimes it's closed. Sometimes it's like water pipe, not necessary to be atmosphere here. We must be careful about what we have here. So this is how we can calculate any equation. This is how we can understand this concept. Look at this figure again here. Same concept, guys. I will do it again for you. I'll make it bigger for you regardless the numbers. These guys, this is the equation here. Okay, so you will know, yeah, this is after, actually after substitution. I will this is our equation. Okay guys, I gonna repeat again this concept. As you can see here, it's I think more clear. For any manometer, especially for multi-fluid manometer, we're gonna start from the left side with B1 here, which is the atmosphere, the air pressure here. Then I will look at the next change of the liquid. So we have oil here and we have mercury here, right? So the next change after one is, I go water, water, water. I see oil here. So this is the level of the oil. So the difference in level between water and oil is H1, 1. So for sure I'm gonna use positive because it's a drop. So B1 plus raw water G1H1, this one. Then I go with oil. The next level is mercury. Mercury is comes also at the lower level, lower than oil. So I gonna use positive again, plus raw oil GH2, this H2, right? Then I look at the mercury. I move with mercury. The ended point here is here at 2, which is higher than the starting point of the mercury. So I use minus here. Raw mercury GH3. All this equal P2, which is atmospheric pressure. So I know by atmospheric pressure I can do the calculate all these three terms. So I can easily calculate P1. Look at this numbers. Be careful about kilonewtons and kilopascal. K is equal 1000. So you either use my method that I show you in the class, or you are using the book method. It's up to you, right? Section number 3, fluid statics. As I told you, we have, when anything statics mean that there is no velocity, fluid at rest. Hydrostatic when we have fluid at motion, right? So this is something to know. Now I need to apply the concept of hydrostatic forces on submerged planes. As you know, we can have like any planes inside water, in any inside liquid, whatever. We have some formulas to calculate what is the pressure. It's very simple, very easy. It's depend on this concept. Rho GH plus, this is gauge pressure, the total pressure, we must add B atmosphere. So I need to know the liquid, then I know rho, then I calculate depth, finish, done. This is the concept about it. So, but you see guys, when we have a plane, when we have plate, we need to calculate something called center of pressure, centroid, and sorry, center of gravity and center of pressure. This is something to help us to calculate the equation. We have three cases actually for this. We can have horizontal plate, we can have normal plate, and we can have also inclined plate. This equation all already described in the class. You are not required to do derivation, but you need to understand this equation. All this done in the class. This is okay. So this is how we can calculate like the second moment of inertia. If we have decline, we need to know the center of pressure, the centroid of the area. Then we have all these issues. This is some examples about the centroidal moment of inertia for regular and common shapes. We have pressure prism, which is like the three-dimensional figure of the pressure. You need to understand this concept. We have here the summary. The summary here, guys, look at this figure. When we have horizontal rectangular plate, Fr is gonna equal B naught, which is can be atmospheric pressure, plus rho GH times AB. AB is the area because this is a pressure, and to calculate force, we must times or multiply by the area. Area here is A times B. We have depth here, thickness, right? If we have vertical, same concept also, Fr is gonna be B naught, atmospheric pressure, plus P rho G times what? Okay, the depth here is, we need to know that the centroid YB, which is gonna be S here plus B over 2, right? B over 2. This is YB. And it could be, if we have the plate at the top here, there is no S. When S is 0, is gonna equal, Fr is gonna be equal P naught plus PG P over 2 times AB. AB is still the area. This is the A, it's like the length and the width of the plate. When we have it in that way, titled or inclined, same concept, but we must include sign in the calculation, right? We mainly avoid studying this case. Okay, so it's same concept. We need to know the YB, then after that we take it from that. This is the equation that you use to calculate YB. I use this equation to calculate all other parameters here. Fi here, Fr, you see Fr, Fr, when we have S0, same equation. It's very similar to the normal one, just we include sign here because we are dealing only with vertical, right? I told you rho GH is not P or S, it's H, normal depth, right? We have this example solved already in the class, and I think all of you understand it. It's about the concept of this, that when we have car sink to the lake for 8 meters, we have high pressure here, comes from the outside. By calculating the force, it will be equal 84 kilonewton per meter square times by momentum. So you see, so this pressure, so this is the pressure that produced by the water here. When I times by the door area, we have 100 kilonewton. This is too much. Can't like normal human being do that force. So the only way to open the car here is to let water go inside. Then we have water pressure from inside, then it can be opened easily, right? Yeah, section 3.5 is not required from you guys. Three six, buoyancy and stability. Very interesting, very nice section. It's depend on the concept of the pressure. When we have a pressure at the bottom side is bigger than the upper side. So just like direct application of that concept, I will give you some examples about this later. So this is the concept of buoyancy. And actually this is not only for in the water, it's applicable also in the air. The balloon is depend on the concept of buoyancy. We described this concept a lot before. You see, this is how is the floating body. We have three cases for any body. We have three cases. We have floating bodies when we have the rho of the body, the average rho is less than the rho of the liquid. And this is how we have in the ship. We make it big and we have a lot of voids inside the ship. That's how we can make the average density of the ship or the boat less than the density of water. This is the suspended bodies. When we have the average density of the ship is equal the density of the liquid. Sinking body, when the density of the thing is more than the density of water. So we have sinking case. So you need to know these cases. We did this example. It's much easier to hold a concrete block from water than air because we have buoyancy force Fp upward. Buoyancy force upward. So how we can calculate buoyancy forces? By the equation here. Same equation. It's equal rho F times G times V. Rho not the rho of the solid or the rho of the liquid, right? Because we need to, let me remind you with the concept actually. What is the buoyant force? It's the upward force that a fluid exerts on a body immersed on it. This buoyant force actually is caused by increased pressure with depth in the fluid, right? So this is, you need to understand. This is a very old and concept in the science. So we're gonna use the volume of the body, G is G, and but the rho is related to the fluid itself, not related to the body itself, right? So that's why here, so yeah, okay. We still have something about stability. We did discussion. We have three cases for stability: stable, neutral, stable, unstable. All details already in the textbook. If you want to go there, we discussed this in details in the class. Okay guys, this is a quick revision for this chapter. In next video I will solve some about 5-6 problems for you, then you will be able to answer the assignment. Okay guys, thank you so much and good luck.